Finally, we want to wrap up emphasizing or re-emphasizing some cautions when you go to study associations or build regression models. Some of these we've already touched on, but I want to briefly address them again because they're super important. First of all, using a regression model to predict values of the response variable based on observations of the explanatory variable that are outside the region of observed values is called extrapolation. This is dangerous. We've already seen that in the case of pricing these Corvettes, right? If you remember that example where you might make some observations in a region and you might build a really good regression model and discover a trend in that region. But this model may be absolutely inappropriate for trying to make predictions when your predictor or explanatory variable is, say, over here somewhere. The truth is, your response variable may actually, if you were to take more data, might actually come up this way. You really don't know the true behavior of the response until you take some data in and around the region of interest for your explanatory variable. The only really valid explanatory variable region for making predictions using this model is right over in here. Okay, so that in the future, if you make an observation of your explanatory variable right there, then you could maybe use the line to predict the response to be right there. Okay, or if you make an observation of your explanatory or predictor variable here, then you could use the regression line to predict the response to be, say, here. Also, keep in mind that these predictions are only predictions. They're not predictions with certainty. Even the very best statisticians in the world can't claim to make predictions with certainty. This trend line here is just that. It's a trend line, and it models the mean response given a value of the explanatory variable. And we don't even know if it's the true mean response. We just expect that it probably is pretty close to the true mean response. You can see that it's not perfect because here we have actual living, breathing data points, and the line just sort of models that behavior. It's sort of a caricature, a simplified version of what's really going on in real life. Okay? Next, also watch out for outliers. Outliers are data points that are far from the regression line, or data points that are sort of far from the trend from the rest of the data. So, for example, a data point over here would be considered an outlier. A data point up here would probably be considered an outlier. However, a data point down here would probably not be considered an outlier. It is still sort of in the trend. Even though it is sort of far from the pack, it's still along that trend there. And how do you detect outliers? We have several ways to think about them now, but within the context of regression, if you can, you want to make a plot, make a visual plot like this, and then just visually inspect. Do you have points that are sort of far from the trend, or maybe way up here somewhere? Or if you can't do that, or even if you can, you want to look at large residual values. Remember, the residuals are just vertical distances between your response variable values and the line. So for example, if I had a point up here, then the residual there is quite large. If I have a point here, the residual there is quite large. If I have a point over here, the residual there is quite large. Influential observations are different from outliers. These are data points whose removal would cause a dramatic change in the regression line. For example, if I had a data point way down here, I might not consider this to be an outlier because it's not real far from the trend. However, now suppose I had another data point that's sort of way out here. If I redraw my regression line, that point's going to have sort of a leveraging effect on the data, I think. Well, I would not call that point an outlier at all because, hey, you know, it's pretty much in the trend of the data. It is an influential observation, because if I went to remove that point, my new regression line would run back this way. Okay? As another example, suppose you have a nice little point pattern running like this, then it looks to me that there's a nice trend going this way. But hey, guess what? Suppose now you discovered another observation over here, and maybe even another one, say, over here. Now drop a trend line across the entire data set. What's it going to look like? It's going to go this way. Remember, the regression line is the unique line that minimizes the sum of squared errors. It's a line that sort of comes closest to all the data points, including these over here. If instead I'd drawn my regression line going up this way, then these points over here would have humongous contributions to my squared errors, right? Because their residuals would run way up there, right? So really this red line fits the data pretty good in a sense. It sort of comes pretty close to most of the data values. I might even have a pretty high R-squared value of like 0.91 or something. However, I can tell by visually inspecting this line is not a good model for the data. Probably a much better model would be something more like this, that sort of comes close to these data points and then also comes down and meets up with these data points. But to truly build a better model, you really need more data. At any rate, these data points out here, I would say, are influential, because if you removed them, your new regression line would run right down and through here. They are not outliers, though. They're not outliers with respect to this regression line. In a sense, though, they are kind of outliers with respect to, this point pattern. So what is an outlier? That's a really good question. The line sort of says that the data point pattern is running this way, but your eye can clearly identify a data point pattern here and then a couple of anomalies over here. So in a sense, you might say that these are outliers, but they are certainly influential observations. Confounding variables, or also called lurking variables, confounding or lurking variables, these are variables that are associated with both the explanatory and response variables. They can explain associations between the explanatory and response, but they might not be at the forefront of your study. It might not even be something that you've thought of. This is why they're called lurking, because they may be sort of lurking in the background. And we've talked about this, large R-squared values do not necessarily mean that the regression line is useful for making predictions. Remember, R-squared is the coefficient of determination, which measures the proportion of variation in the response variable. It's accounted for in your regression model. Now, remember, R-squared, the coefficient of determination, is in fact little r squared. So if I were to take this number, which turns out to be the r value for each one of these 1, 2, 3, 4 data sets, what is r squared in this case? It's 0.6659 approximately. Okay, that's not too shabby. It's not, it's not like 90% or anything. But hey, here's the point that we want to make here. Our coefficient of determination is 0.6659 for all 4 of these. Okay, different plots can have the same r squared values. Look at this one. In this first one, that's a nice trend, right? It looks like maybe this line could be useful for making predictions somewhat. R squared is 0.67. Okay, however, look at this plot over here. Clearly, there's, a better model would be something like this, that sort of curves like this, maybe using quadratic regression. Okay, however, I get the same r squared value. I get the same r squared value. What about in this case? I get whoa, look at that. Clearly, this point is an outlier. Maybe we should be examining what's going on there. It's also having an influence on the regression line, right? Because if I got rid of it, the line would swing this way to match up with these points a lot better. But still, this has the same r squared value as all the other ones. And finally, this one also has the same r squared value. In each of these 1, 2, 3, 4 graphs, the regression model, or the linear regression line there, captures about 67% of the variation in the response. That's pretty good. But you know how they say a picture's worth 1,000 words? Yeah, especially I think in this case right here. This is probably a terrible model. This is probably a terrible, 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 terrible model. We also talked about this example before, but let's revisit it. Ice cream causes drowning. Okay, so some students at Purdue University some years ago, I think, wrote an article on this. They collected some data on ice cream sales and deaths due to drowning. And the data looks something like this. Well, there are a couple things going on here. First of all, ice cream causes drowning? Absolutely not. They did an observational study, okay? They did not carry out an experimental design. That would be highly unethical, right? This was an observational study, and in observational studies, the best you can do is claim association, not causation. So this is another thing to keep in mind, another caution when you're doing association and regression, is that association does not imply causation. It's a fact that consumption of ice cream or ice cream sales is associated with drowning deaths. But what's really going on here is, remember, there's a lurking variable in the background, which is the season, right? We talked about this. As it warms up outside, people tend to buy more ice cream. They also tend to go to the pool, go to the beach. And unfortunately, when they go to the pool or the beach, we see more drowning deaths. Finally, let's take a look at one more example. Here I've got numbers of AIDS cases, syphilis cases, and tuberculosis cases. These are confirmed cases, that is, in every state in the United States for some year. I forget, I think it's the year 2000. Okay, and so I tell you what I'm going to do is just to sort of explore the data a little bit. This is the first thing you maybe want to do, aside from cleaning it. Maybe take just start looking it over and make some charts and graphs. Start exploring your data. It looks like my states are all abbreviated and put in alphabetical order according to their state abbreviation. Let's see, it looks like, okay, there are 52 states. I know that's not right, so what's going on here? Let's see. Okay, well, first of all, so here's DC, the District of Columbia, so maybe we'll leave that one in. But also, last row here is all, says all states, so I know that's going to be a problem. For example, let's just make a scatter plot. I've got 3 quantitative variables here, right? AIDS cases, syphilis cases, and numbers of cases of tuberculosis. So maybe I'll just do a simple one here, and plot, let's say, AIDS versus tuberculosis, okay? Whoa, look at that. Is there a linear trend? It's kind of hard to see because, hey, look, this point out here, it may be an outlier or certainly influential. What is this? This is for all cases. In fact, if I hover on it, it says, yeah, that's row 52. So I tell you what, I need to get rid of that. It's going to obscure any kind of point pattern for the rest of the data values. So I'm just going to come in here and I'm going to delete that stuff. And I'll even delete this graph and go back and do it again. Let's make a scatter plot, simple one. Again, AIDS versus tuberculosis. Okay, now that has a little bit more meaning, I think. Certainly looks like as tuberculosis cases increase, AIDS cases also increase. Let's put that to the side, and now let's make a graph of syphilis cases versus tuberculosis cases. Okay, here is tuberculosis cases increase, syphilis cases also increase. And there seems to be a pretty good linear trend this way. Maybe there's an outlier over here. Where is this? This is row 5, which is California. Okay, in California for that year, for some reason, it looks like for the number of tuberculosis cases, the number of syphilis cases was a lot lower than you might expect by looking at the trend for the rest of the states. Okay, that's interesting as well. I'll put that to the side. And finally, let's make one more graph. Let's plot, say, AIDS versus syphilis cases. Okay, AIDS cases versus syphilis cases. And what do you notice there? Sure enough, yep, same kind of trend. As syphilis cases increase, AIDS cases also increase. Now, what do you think might be the causes of these trends? Remember, all we have here are associations. It doesn't even really make sense to argue about which variables to put on the x-axis and which variables to put on the y-axis. This was not any kind of experimental design. This is just a mere observational study. People carry these things out all the time in order to inform public health officials. But what might be causing this stuff? If you take a second to think about it, maybe it has something to do with sexual activity. I mean, I know that AIDS and syphilis are sexually transmitted diseases. Is tuberculosis? Well, no, I don't think so. But you know what? When people are having sex, they're also in very close proximity. And so maybe that's how they can get tuberculosis. So hey, maybe this makes sense. Maybe it's all tied to sex. When I give this data set to my undergraduate majors or even graduate students, that's by far the mode response. However, there's really something else going on here. And if you want, maybe you could pause the video and think about it for just a second. What I'm going to do is I'm going to go and get the populations for these states. And this is how I'm going to do it. I think these data were from the year 2000. It's not going to matter so much. But all I did was I'm just doing a Google search for state populations 2000. And this is what I get. 2000 United States Census. And if I scroll down, then I'll see the data right in here. You can sort them by rank according to size, smallest to largest or whatever, or by the state abbreviation. Okay, that's what we want, so I'll go ahead and do that. And then I'm just going to go and highlight all this stuff. Data is just all over the web these days. I'm going to Control C to copy that, Control C, go back to my menu tab over here. I'm going to see if maybe I'll get lucky and I can just paste that stuff in there. Hey, look at that. Control V. That's how I can paste. Now, I got to be careful here. Remember, these are my ranks, and these are my state names, and these are, let's see, you know what? I don't even need these columns. I'm just going to get rid of them. And these are 1990 census figures, and these are the year 2000 census figs. Okay, so column 10 there is really what I'm most interested in. I got to be careful here. I got to make sure that my state names match up with my state abbreviations there, right? So I got Alabama, Alaska, Arizona, Arkansas. Oh, see, these are flipped. AR is the abbreviation for Arkansas, and AZ is the abbreviation for Arizona. So, holy smokes, I better fix that. Okay, we got California, Colorado, Connecticut, Delaware, DC. These also need to be flipped, right? This is what you call cleaning the data. Florida, Georgia, Hawaii, Idaho. Oh, these are all out of order. Got to fix those too. What a pain. I'm just going to shoot through here and fix all this stuff real quick. Done. So it looks like now I've got everything in order. You've got to be really careful about that. Now let's do something interesting. Let's plot AIDS cases versus the 2000 census figures. Holy smokes, look at that. That looks like a pretty positive association there. Let's also plot syphilis cases versus the 2000 census figures. Another positive association. And finally, guess what? If you plot tuberculosis cases versus the 2000 census figures, you're going to see another positive association. Okay, really the culprit here is the sheer size of the populations in these states, right? The more people you have, the more AIDS cases you're going to have, and the more tuberculosis you'll have, and the more syphilis you'll have, the more automobiles you'll have, and the more houses you'll have, and the higher your ice cream sales figures are going to be, and the more deaths by drowning. So population size here, I think, is really the lurking variable. How do you identify lurking variables? Oh, that's a good one. Lurking variables are not always easy to identify. You just have to think and use your brain. What could be causing this? What could be causing that?